I believe the cause was a combination of fuel shutoff valve, FSOV, activation due to a cascading electrical system failure. It's not the first time the 787 has experienced electrical cascade system failure during the first minutes in flight and required RAT deployment. Let me explain my reasoning. On the Boeing 787, the engines will keep running even if all hydraulic systems fail. Each engine has its own FADEC, full authority digital engine control, powered by a permanent magnet alternator, PMO, that's driven by the engine itself. Once the engine is spinning, the FADEC operates independently, controlling fuel, thrust, and safety, with no need for aircraft hydraulics or external electrical power. A simultaneous FADEC shut down if they are supposed to be so resilient. There is one important component that can override the FADEC, the FSOV. This spring-loaded fuel shutoff valve is not powered by the PMO, but instead by the aircraft's electrical DC system. If power is lost, the spring closes the valve instantly, cutting off fuel to the engine. FSOVs are a fail-safe, designed to protect the airframe, not the engine. In Boeing's logic, it's safer for the engine to shut down than to keep feeding fuel into a potential fire. In the video footage, the truck tilt actuator is in the forward position, toes down. This movement requires a hydraulic system force to overcome the wind and gravity. This forward position only happens when the landing gear retracted sequence is only the second step of the main gear retraction sequence to tilt the wheel truck forward. The first step is to open the doors, and if the doors are fully open, the next step is to tilt the wheel truck. It's unclear why the doors are closed, but the truck already tilted forward. Most likely the pilot selected gear up, which triggered the retraction sequence. The truck tilt was initiated as step 2, but the doors didn't open due to power or hydraulic failure, or the sequence froze mid-process. The aircraft lost main power, hence the RAT, and the sequence halted with the gear in a partially commanded state. Truck tilted, doors closed may have been the exact point when the whole system collapsed just 3 seconds after takeoff. There was a positive climb rate at 600 feet AMSL and 174 kT. The engines kept running briefly, 3 seconds, powered by the remaining fuel in the lines before flaming out. The main landing gear hydraulics are powered by an electric hydraulic system. If there's no electricity, there's no hydraulic pressure. In contrast, other hydraulic systems on the aircraft are supplied by engine-driven mechanical pumps, 20-30 kilowatts stable in flight. It's likely that both engines flamed out simultaneously. Flaps, fly-by-wire, landing gear, and other systems likely froze for a moment, and possibly regained functionality after the RAT deployed. The +15 kW RAT powers the electric motors on the blue hydraulic lines of a 787. This controls the key flight control actuators for the rudder, elevators, and primary ailerons. It appears that the pilot slightly increased the nose attitude during the final phase of the flight. Landing gear retraction is not possible with a RAT. For both FSOVs to close, the aircraft would have to lose both AC buses, both DC essential buses, and the battery backups. That requires a massive electrical failure to overcome all possible redundancy layers. This is a possibility because there are known cases where a 787 and a 777 experienced a total electrical cascading failure of most systems, cut off by the FSOVs. The big question is, why did they fail? This is hard to say, but as said, electrical failure is a very plausible cause. The RAT was automatically deployed. This means there is a total loss of AC electrical power. I suspect a scenario where a partially working or unstable electrical system triggers RAT deployment amid a power transition event. This could escalate into a full-blown electrical disruption, possibly interfering with the DC essential buses and battery backup. When switching power sources from main buses to RAT, the system can behave unpredictably, especially if one source is competing with the RAT or is unstable. In such a power chaos, RAT deployment might introduce transients or delays in power restoration, which could make power delivery unstable and possibly affect the digital managed power to the FSOVs. If they lose power, all FSOVs don't have guaranteed dedicated or hot battery backup, unlike the Airbus AE320, which powers them directly from the battery. The 787's battery backup supports the entire DC bus, and power management software prioritizes flight-critical systems. If power is limited or loads are erratic, less critical systems like FSOVs can be deprioritized. This is a very complex system with a lot of software rules. This also reflects Boeing's design philosophy. In a severe power failure, airframe survivability and flight control take precedence over engine continuity. Their assumption is that it's safer to shut off fuel than risk uncontrolled flow into an engine on fire. The whole idea of the possibility of losing both engines at 400 feet during takeoff feels inherently unsafe. From a thrust continuity perspective, this design approach is a vulnerability and may have played a role in Flight AEI. There are no documented cases of a modern Boeing experiencing an engine flameout from FSOV closure due to an electrical glitch. The 787 and other Boeing models have a history of similar electrical issues. In 2020, for an Atlantic Boeing 787 flight, VS-105, during climb out, the crew experienced a major electrical failure. Engine generators dropped offline. In response, the RAT automatically deployed to provide emergency power. In 2015, Boeing and the FAA discovered a critical software bug in the 787's generator control units, GCUs. If left powered for 248 consecutive days, an internal counter could overflow, shutting down all 4 GCUs and cutting AC power entirely. The FAA issued Emergency AD 2015-0851, requiring operators to reboot 787s every 8 months to avoid in-flight total power loss. 2 separate incidents, in Boston, JAL, and Takamatsu, ANA, involved battery overheating and fire in the aircraft's LATAM Flight LAE 8084, a Boeing 777-300er, suffered a complete electrical meltdown en route from Sao Paulo to London. The RAT deployed to provide emergency power. Once the engines were shut down on the ground, power suddenly returned, confirming a fault in the electrical distribution system, likely a bus contactor or converter failure. The event was a textbook cascading failure. Generator power was available, but a chain reaction of breaker and converter failures disconnected all major buses, including those powered by the APU and engines. The 787 relies heavily on software-based power management, so if the root cause turns out to be a software flaw in an extremely complex electrical system, the entire fleet could soon be grounded. Modern jet fuel systems are pressurized and temperature managed, making vapor lock rare. For both engines to fail simultaneously from vapor lock would mean identical thermal, pressure, and fuel conditions in both lines, extremely unlikely.